Hello everyone, welcome to lecture 19 of this course. In the previous lecture, we discussed Curry-Harvard correspondence, the motivation of this correspondence, and discussed the intuitionistic implication of logic. Today we are going to discuss the correspondence in more detail. Now in untyped lambda calculus, there is only one universe, namely the terms. In typed lambda calculus, there are two universes, terms and types. So when we write M has type tau, it is a sort of binding the two universes. These two universes are independent of each other. So this creates some sort of binding. Now what happens with this binding? So we have seen that there is a system T lambda where we can write a formula of this form. This means that in a given context, the term M has type tau, and in context means all the free variables of M are defined in this context. Now this formula, we can give a deduction in T lambda. That means if say the context is empty set, then we can give a deduction of this formula. That means that M has type tau, we can give a deduction using the deduction rules and this set of axioms. That means we can assert, this deduction asserts that indeed M has type tau. Now consider this problem that we are given a type tau and we are asked to find or to determine whether there is a lambda term M that has this type gamma tau. So we are given tau and we are asking whether there is a lambda term M that has type tau, or we can say that can this type be assigned to some lambda term M. Now if you examine T lambda carefully, then we find that there is no way to obtain this M. M we cannot obtain. The deductions are based on that if we have the knowledge of M and tau and some context, then the deduction we can give. But now that this is incomplete, that is information is missing here, the M is not supplied, we cannot proceed, and this answer is not, we cannot determine this thing in T lambda. So then how to address this problem? So the one way of addressing this problem is the types that we have, say a type that is coming from some type language. So our language was, one is we have an atomic type. So we say type variable is of atomic type, is a type. And if sigma and tau are types, then sigma arrow tau is a type, and that is called a composite type. This is that language of T lambda. So all the sentences that that we are calling as type. Now what we are going to do, this type tau, we are going to give an interpretation of the type. That means a meaning of the type. That means now type, we will look this type, this say for example A, we will look at it as a proposition of some logic. We will view this type variable A as a proposition of some logic. And the composite type sigma arrow tau will be looked upon as a logical implication in the logical language. And we have seen that this logical language that we have here, this type language and the logical language that we have already studied, this is that IL. IL is this. So every sentence that we obtained in the type language of T lambda, we have a corresponding formula in the logical language. The interpretation is simple. If I have sigma arrow tau, I will interpret this as an implication. Sigma implies tau. Now this logic is well known and it is well understood. By this we know what is the proposition, the truth of a proposition, what is the meaning of this, that this is provable. This concept we know. That means if this is provable, then we know there will be a proof of this. How to do this proof, that is also well known in this system. So now we have a system that is a logic. Our system is logic. This is one system, that is T lambda. So these are different things. So now we are trying to connect, by the interpretation we are trying to connect. That means now suppose we have asked the question, given a type tau, does there exist a lambda term for this type, or can this type be assigned to some lambda term? Now we are after interpretation, so then this tau is a formula in a logical language, say IIL. We know IIL very well. Now we try to give a proof of tau in this language. Suppose it goes through. So, we have a proof of tau in IIL. From this, what can we conclude? From this, we can assert that there exists some lambda term m such that tau can be assigned to m. This is something that we have now obtained. Earlier, we were not able to answer this question. Now, what the first thing we have done, this asserts that there exists some lambda term m such that m has type tau. This is our first thing that we have obtained. Next question is, what is this m? We do not know. We say, okay, there is an m that will have this tau, but we do not know what is this m. So, again we need to do some work. Now, do we really need to do some work or not? That is the question. Now, the nice thing is that from this proof that we have obtained of tau, we have a proof of tau. This proof structure is actually, from this proof structure or from this proof, we can obtain this m. Now, proof looks like formulas and all. So, what we have to do? We have to do some syntactic transformations on this proof. The structure of the proof will not be altered in any way. We have to make some syntactic transformations. This is all we have to do, and then we can get that m. So, this means we have synthesized a program from this proof of the type tau or the formula tau. That is, that interpretation has helped. That means the writing a proof then means writing a program or a lambda term in T lambda. This is the whole idea about this Curry-Harvard correspondence. We can also go from this T lambda system, that means the type lambda system, to this logic system as well. This is what we are going to discuss today. So, this then leads to the connection. So, the interpretation says that we are now viewing the types as propositions. Propositions and types, that connections we have established. That means we are now understanding types. We are saying, look, we are going to view types as propositions. And if I have a proof, that means this coincides with the terms, and this is the correspondence. So, now this correspondence says that propositions are types, either way. So, there are two systems, one is a logic system and another is a language of types or the T lambda system. Either way we can view. If we say I have a type, I will say I have a proposition. I have a proposition means I have a type. So, these two corresponds. So, now I have a proof of a formula. So, tau is a formula, I have a proof. That means I have a program m that has data type tau. So, thus we have these two systems, logic and programming. Logic means natural deduction, and programming in this sense is lambda calculus and type theory. So, we start with the proposition A. The correspondence gives it is a type A, or we start with either way. So, we can either way. Either we start from logic and move to programming, or we start with programming and go to logic. So, let us say we are going from logic to lambda. The proof of A means we have a term T that has type A. A term may be a program or an expression. Next, A implies B. Logical implication in logic then translates to a function type A arrow B. That means the mapping from type A to type B. Now, when we say we have a proof of A implies B in logic, this means we have a function lambda x dot t, where x has type A and t is a term. This is the correspondence that we have. And then what we have, these deeper things that we are obtaining here. Doing logic means, that means when we are giving a proof, it means we are writing programs. That means we are synthesizing a program. And when we are programming in a type lambda calculus, it means we are proving theorems. And then checking a proof means type checking a program. This is the whole idea about this correspondence. Okay, now that we have got some intuitive feeling about the correspondence, we are going to give an example that illustrates the plan of our work. That means today's discussion, how we are going to go through. This is what we are going to illustrate through this example. So, we are saying logic to lambda or lambda to logic, whichever, both way we are going to do. So, consider this formula tau, that means this is a type in simply type lambda calculus. So, we are given a type tau, that means we are given a formula tau in IIL. We also have a proof of tau in IIL. This is already given to us. This part is given. So, tau is given, type is given, that means a formula is given. We also have a proof of this formula. Now, the question that we asked is, What is the meaning that this type or this formula has a proof? This correspondence asserts that there is a lambda term that has this type t, or type tau can be assigned to some lambda term. This lambda term is this. This is the lambda term that has type tau. Now we said, how can we obtain this lambda term? This is the next question. Given this structure, so you see, if you look count these lines, 1, 2, 3, 4, 5 things, 6, 1, 2, 3, 4, 5. So 6, this structure will be maintained. We are not going to alter in any way. Only things we will make some annotations. So let us see how to address that. Now, how did we obtain the term this for the type tau? That is the question. So now this is the term. You may ask, how did we obtain this term? So we have this proof. So this proof we had, remember that this is the proof. We are going to now obtain this. So this is the transformations we made. So here we had this part. Now we created this bigger type annotation. We had this, we created this. Similarly, we have done 1, 2, 3, 4, 5, 6. There are 6 as it is. So the structure of the proof is not altered, and as a result of this, we have constructed, that means we have synthesized a program from the proof. This is now the program. This is what we obtained. Lambda y dot lambda z dot lambda x, z x y, this has type in T lambda. This is a deduction in T lambda. So this answer, that question that we asked, we have got an answer via this correspondence. And once we make the interpretation of types as formulas, then these things will go through. Now suppose we have this m has type tau. M has type tau is given to us, suppose. Now what does that mean? That means we have a deduction. This is the deduction of m has type tau in T lambda. Now what does that correspond to? That corresponds to the fact that this type now is interpreted as a formula. That means this formula is provable in that logic II. Now what is that proof? Again we will ask the question, what is that proof? Again we make syntactic transformation. That means we will, as if there is an eraser function that erases the context, that erases the subject and keeps only the type. So that means all these things are omitted, we have only these parts. We have only these parts and we will get this. So what we have seen is that we have done two things. One is we have transformed a proof in logic to a lambda term, and another is a proof in T lambda to a proof in logic. These are the two things we are going to discuss today. So now we will discuss this correspondence, and it has two parts, logic to lambda and lambda to logic. So the notation that we are going to use, we write delta L when we are talking about a deduction in logic, that is IIL, and we like delta lambda when we are talking about a deduction in. So the definition of logic to lambda is like this. So we will give it in, there are three parts, means point 1, point 2, point 3, based on the structure of the formulas. So if delta is an IIL deduction, then the corresponding T lambda deduction, delta lambda is defined as, so first is that delta is a single formula tau. Then delta lambda would be x arrow tau maps to x arrow tau for some term variable x. So for example, in our delta we have say a arrow b. That means delta lambda we have to use some term variable x. So x is our term variable. So this is, if it is a single formula, delta lambda will be this. Now we have to consider the, when we have arrow e. If the last step in delta is arrow e applied to the conclusions of the deductions delta prime and delta double prime, and their corresponding deductions in T lambda are delta prime lambda is P has type sigma arrow tau and in the context gamma prime, and Q has type sigma in the context gamma double prime. Then delta L is obtained by applying arrow E of T lambda to these two deductions, and we will rename the term variables in delta lambda double prime so that there are no common term variables with delta prime lambda, neither free nor bound. So we will see how this can be done. So we have said delta prime, this is a arrow b, and we have delta double prime, this as a. Now delta prime lambda, we can say x is a y, a arrow b maps to y, A arrow B. This is already there, and delta double prime lambda is X as A, X as type A. Now we are applying these to delta prime lambda, delta, it should be delta, here, we have a delta here. So this is delta, so corresponding is delta lambda. So this is, we are doing now arrow E. So if we do arrow E here, because these variables are all distinct, so consistency will be preserved. So gamma 1 union gamma 2 we are going to get, and this is map, so it will be Yx as type B. This will be the deduction in A lambda. Now we have to consider the arrow I case. Okay, if the last step in delta is an occurrence of arrow I with the form, so it is in IIL, the structure is, we are assuming rho and we are deriving, so this part is a deduction delta prime. So we are deriving sigma, that means by that rule we can say rho implies low logically implies sigma, and then we will discharge all the occurrences of sigma. That means it may be this assumption that we made here, it may not be at 1, it is 0, that means we are doing vacuously. Otherwise, if it is say 1, that means only once here, the assumption was made once. But if it is more than once, then we are discharging all of them. That means when we are introducing this arrow I, all these assumptions are discharged. And the conclusion of delta prime lambda is, this is then the conclusion. So what we have P has type sigma and the context is gamma, and so for each one of them we have a distinct term variable V1, V2, Vk. All of them, V1 has type rho, Vk has type rho. They are all distinct and they occur free in P at the same positions as these rows occur in delta prime in this deduction, and each Vi is occurring only once in P. Now the idea is we will make a substitution that each Vi is replaced with X, a new term variable that is not occurring anywhere in this. And then if we do this, then it will become X as rho, all of them X as rho, then by union it will be X as rho. So this will be the modified that conclusion that we had here. This is now transformed to this, and then this substitution we are going to get here. So we are writing P prime here because this V1, V2, Vk are occurring in P. As a result of the substitution, they will be replaced by X. So that is why we are writing P prime. Then we are going to apply arrow E in T lambda, and that by virtue of that we are going to get lambda x dot P prime. P prime has type sigma, so it will be rho arrow sigma. This is the idea. And if there is no occurrence, then it will be vacuously. So these steps we don't have to do. Vacuously we are going to get. And vacuously we are saying that rho implies sigma. Now this needs a little discussion that why at all. First, we have not seen examples where we have multiple such assumptions. We might, if we recall, we have seen perhaps only one, maybe one example we had where we had say A was assumed at 2 places. So even if we have it, for this deduction we have to now understand that if say A is assumed at multiple places, so then why this we are replacing all of them with one variable X. This needs to be illustrated here. So we are going to see, so we will work it out as very small situation. So we do this. So we say we have made an assumption B here at a deduction, and here another place we have made a deduction, and this is here. And then T lambda, then what we are going to get? We are going to get X as type B, and here we are going to get Y as type B. Now say we have here D, and then by arrow E, arrow I, because we have assumed B, so we can obtain D. So B arrow D, this part we can get, and we are writing here discharge B at star and double star. This is what the rule says. Now when we have this, that means in this TA lambda what we have here, TA lambda, this is coming in the corresponding TA lambda, it will be, the context will have x b and y has b, and then you have something here, these x's are occurring to get a lambda term. Now the rule says, now this rule says that look, we have to unify these x and y and we have to make it same. That means say x and y are replaced with r. If that be the case, we will get r has type b, and we are going to replace here also the occurrences of x, y with r. Then if we do this, the arrow I says we are going to get b arrow d. Now here that means this r has type b in TA lambda, that means r has b, lambda r dot this part will get the type b arrow d. This has type d. This is the whole idea here. This is what we are doing. So we need to make this unify x, y and create r. Now suppose we don't do. Suppose we say no, we will not do this way, but we will do this arrow I separately. That means I will first discharge x. That means I will have say discharge y first. So discharge y will give me something. I will get lambda term here. Then I will do again arrow I first. That means I will get lambda x first. That means in TA lambda, this is arrow I is one step, arrow I of logic. Now in TA lambda, we have two steps. One is for this y and another is for this y. That means now the proof structure in TA lambda has changed, and the number of steps, if we count this, then it is increased by 1. So the term that you are going to get, that will be different. Hence, that is the rationality of saying that, okay, if you have this many occurrences and you are saying discharge b at this, that means you are saying as if that these are all the same thing, x, y, z, whatever might be, they are the same term r, and then we are doing this. Moreover, then the next question is, when we are doing this substitution, what happens to this term here? Are we getting a new term? Whatever we had earlier, we had p, and now we are by the substitution we are getting p prime. Are these two terms equivalent or not? That is the second question. Yes, they are equivalent, because what we are interested in is here the types that we are going to get as a result of this transformation. The types are not changed. So arrow E has not been changed in any way. So arrow E does not change means that even if we change these names of the variables, it will not create any problem at all. Thus we have this rule. Thus we see that when we have this sort of thing, that multiple places when we are assuming row and we are saying or remove all of them, you are doing remove all of them. If you are saying there could be a situation where I am saying discharging sigma from some place star, then it will be only one discharge, arrow I. Again, if I do discharge sigma at another place, then another arrow I, then another one step is increased. That part will go accordingly. That if we have only removing one at a time. But once we are saying all of them, that means this thing that we have done, the substitution, that is correct. And that is how it should be. So this is the rationale behind this definition. Okay, now we illustrate the definition of moving from logic to lambda. So we are given a proof of tau, the formula tau, and our goal is to construct a term M such that M has type tau. So this is we are at this stage, line 1, this point. So every transformation we are going to show in red, and we are going to do one step at a time. So step 1, so we had A arrow B and A. So after type annotation, as per the definition, we said the context is y is a type variable, y is a term variable that has this type, and in that context y has type A arrow B. Similarly, x has type A in that context as per the definition. Next, arrow E, that means now it will be this arrow E, then now it is arrow E of TA lambda. So now we are in TA lambda. So it is arrow E of TA lambda. So now we are doing application we are doing. So y is A arrow B, x is A, so yx is of type B, and it is consistent because the variables are all distinct. Then again we had this formula BROC. So we have introduced a new variable z, and z is type BROC. Now you see y has type B, z has type BROC. So arrow is applicable, it is consistency is satisfied. So we will get ZYX is, the term will be ZYX, and that has type C. Now we are discharging A. Now it says, now this part is the IIL part. It is IIL says that we are discharging A. Discharging A at star star star, that place that was there. That means we see where that A is assumed and what is the corresponding variable that we have done there. That means that corresponding variable here will be removed when we do arrow I in IIL. So now when we do arrow IIL, this x that we had here, this x that was there, that has been removed. And now you see that x is not there. This x, it is that star star mean this one, and this x is removed here in arrow I mean. It is only one occurrence, so we have removed it here. Similarly, we do for the other at BROC. BROC is defined at this place and AROB is there. So we go along in the similar way. So we discharge Z, then we discharge this Y, and we have got this lambda term. So this is the lambda term corresponding to this that we have obtained by syntactical transformation of the proof of the formula. So the observations are, at each step a formula of logic is replaced with the formula of lambda. The number of steps in lambda is the same as the number of steps in logic. The structure, that is the proof tree, remains same in both the deductions, and the lambda deduction is a syntactic transformation of the logic deduction. Okay, now we give the definition for moving from lambda to logic. So delta is a TL lambda deduction of this formula. M has type tau in the context gamma. The corresponding logic deduction is defined as, again we go by the structure of the lambda term. So M is a variable and delta is this x has type tau in that context. Then delta L, that means the deduction in logic will be simply tau. That means we have x has type A, this is in delta, and delta L will be simply A. This is in logic. Now this M is of the form PQ, and the last step of delta is, delta prime is P has type sigma arrow tau in the context gamma 1, and Q has type sigma in the context gamma 2, that is the other deductions. And we have arrow E, gamma is gamma 1 union gamma 2, that is consistent, and PQ has type tau. Then delta L is obtained by applying E to of IIL to these corresponding deductions. So that means from this deduction delta L prime, suppose from delta prime L we have obtained A arrow B, and delta double prime L we have obtained is A. Now we will do arrow E of this logic and we are going to get B. This is what it is saying, then this is this part. Now when the structure of M is an abstraction like lambda x dot P, and tau is of the form rho arrow sigma, and the last step of delta is, that means we have P has type sigma in the context gamma, and then we are doing arrow I, and as a result we are getting lambda x dot P that has type rho arrow sigma, and that the context will be gamma excluding x. Then the rule that it says that delta L is obtained by applying arrow I of IIL to delta prime L. That means the corresponding deduction of this part, and discharge all occurrences of rho in delta prime L whose positions are the same as the positions of the free occurrences of x in P. This is what this rule says. So that means what? If we have, say, if I have rho is equal to A, and this is, and we have A assumed at another place, and we have come across, we derive B, that means in logic we are going to write A arrow B, and we will say discharge A at these two places. That means here we have this rho arrow sigma, this is A arrow B. This is what this rule says. So now we are going to illustrate this definition of lambda to logic using the example that we have taken earlier. So we have now a deduction of TL lambda of this M has type tau form, and our goal is to obtain a proof of tau in IIL. So we will do again stepwise, and every step will be colored red. So now this is our first point. So we will get the corresponding thing. That means idea is, if it is simply this part is case 1, so we'll just write A and A arrow B there. So we will have this. This is omitted. So we are going to write A arrow B and A here. Now we are going to apply arrow E of IIL. So we are going to get this B. That means this will be removed. So this is removed. Now again this part is the step 1. That means it is just a variable has type tau. X is a M is a variable. So this part will be omitted. So we are going to get this B arrow C. Now arrow E will be applied, and we are going to get C. This part is omitted. Red part is omitted. Likewise, we have now discharge A at star. That means we are doing arrow I. That means this part, this X, this part's context will be removed. So we are getting A arrow C. So that means now we are writing discharge A at star. This of lambda, arrow I of lambda corresponds to discharge A at star. Next we have to do this part is there. Now we are doing B arrow C. Then B arrow C part is introduced. B arrow C is introduced. That means the Z part has this type, this B arrow C. So this will be removed. So we are going to get B arrow C arrow this. Now this again there is this part we have to remove this Y. Y has type this. So then this discharge we have to make here in the logic, and discharge B. So here we have to write discharge. Here we have to write discharge and discharge A arrow B at this point. This completes the proof, and then what result is that this part we have not shown here. So that means this is omitted. This red part is omitted. This part, then this is the proof of tau. So the observations as we move from lambda to logic, at each step the formula of lambda is replaced with the formula of logic. The number of steps in logic is the same as the number of steps in lambda. The proof tree or the structure remains same in both the deductions, and the logic deduction is a syntactic transformation of the lambda deduction. Now that we have seen the transformations from logic to lambda and lambda to logic and the correspondence, that was the Curry-Harvard correspondence. Now we discuss the implications of the correspondence and what we get out of this correspondence. Now if there is a proof of a formula tau in the logic, then there exists a lambda term M, where M has type tau. This means that if a formula is provable, then the formula when interpreted as a type can be associated with some term. Next, if there is a proof of M has type tau in TL lambda, then tau is provable. This is coming from the constructions. Now earlier we stated this theorem and we showed that every BCK lambda term is typable. Now we are actually trying to say what are the type of terms that are typable. Now it says if it is a BCK lambda term, then it is typable. It is not that, it is not if and only if. That means all typable terms are in that class BCK. So we say that there is one lambda term which is not in BCK. We have shown earlier that it is a S combinator, and this is this lambda term. This is not in BCK. That means BCK then is a proper subset of the set of typable terms. Next, the types of typable terms. That means if say M is typable, that has a type tau, that will correspond to a provable formula in IIL. Now we say what are the things that are not typable or not provable. There is a lambda term that has no type in TL lambda. We have seen this, that is a self application SA, that is lambda x dot xx. We have also seen that there is a formula in IIL that is not provable, that is the Peirce's law. That means the class of non-typable terms correspond to the class of non-provable terms, non-provable formulas. So this assertion is a conceptual analogy. That means certain things, so you have two systems, one is a logic and another is a lambda. So we say that look, this formula is not, certain things that are not provable here, and there in other systems certain things are not typeable here. So these are the two things that cannot be addressed. So these are certain things that cannot be addressed. That is this analogy. This is a conceptual analogy. So as a result of all this, what we have established is that the fundamental connection between these two systems, one is the computation, another is logic. Computation means terms with types and logic is provable formulas. These two things we have connected, or the correspondence, Curry-Howard correspondence gives us this connection. This is the main idea about the correspondence. So now we can give a diagrammatic view of what we have stated in the implication. So we can say that we have a system. So this is our say system TA lambda, and this is the lambda terms. And now we say this is our BCK, and now this is our S combinator, and we write these are non-typeable and these are typeable. This part, this is our non-typeable. And here in this other system, that is we have formulas, that is the terms are interpreted as formulas. So we have this is, so here we have these are the things that are provable and these are the things that are not provable, and this is the system IIL. And this is here we have an instant of Peirce's law, and this is where you have an instant SA, and here this S corresponds to some type and that type is coming here both ways, and BCK we have this way. So this classification is what is obtained. This system you can say computation, and this is logic, and this is what we have M has type tau, and this is the logical formulas. So certain things that cannot be resolved here in means that if this law or the formula cannot be given proof, that means we cannot assign to this formula some type. This is what this the non-provable coincides with non-typeable. SA we have shown that SA lambda x cannot be assigned any type, doesn't have any type there. So this is the idea about the correspondence. So to summarize that, with this we have got some idea about the Curry-Howard correspondence and the transformations in both the directions. So you are requested to see chapter 6 of Hindley's book Basic Simple Type Theory. So with this we stop. Thank you for your kind attention.